So, okay, last time we discussed cohomology groups with coefficients in sheaves. So that is the check homology. And today we will see a very important theorem regarding sheaf cohomology, which is so-called abstract the Rham theorem. So to do that, so let's say the main topic of today is the abstract the Rham theorem. So I'm not gonna state it immediately. We need to do some work before. So let's start with that work. So again, all of this doesn't need to be done on a manifold. We can just take any compact Hausdorff topological space. And we just take a sheaf of abelian groups on it. Groups on X. Now a resolution of the sheaf is a family of sheaves Fj, Jn of sheaves of abelian groups on X such that there are morphisms phi go from F to F0, and then Fj that goes from Fj to Fj plus 1 for all j greater or equal to 0, such that 0, F, F0, Phi0, F1, Phi1, F2, etc., is exact. So that's what we call the resolution of a sheaf F. It's simply a sequence of sheaves that makes all of this exact. And if the cohomology of all these sheaves is 0, so this is for all j greater or equal to 0 and k greater or equal than 1, we can never really expect that H0 is 0, because this is all simply the global sections of the sheaf. But if all the higher cohomology groups are 0, then we call this an acyclic resolution. Okay, what is this about? So for instance, if you have such a resolution and you apply the global sections functor, let's call it like that, we have a cohomological complex you just take global section of each of these sheaves and we get this object here. Since this is an exact sequence, the composition of any of these two is 0, meaning that the kernel is contained in the image. But we don't have, of course, that the kernel is equal to the image. So this might be not exact, but it is still a cohomological complex. If you remember, we do know that this functor of taking global section is left exact. So the first map, if X is injected, and we also have that at this stage, the sequence is exact. So the image of X is precisely the kernel of V0X. Yeah, because if you remember, if we have just a short exact sequence, then you have that if you remove the final 0, that is exact as well. Okay, which means precisely this. So this is another way. So, okay, we have a sheaf, right? We have to build the resolution of this sheaf. So this is another way to construct some cohomology starting from a sheaf. Of course, I mean, you also need a resolution. So let's give it a name. So HKF dot, the cohomology of this complex of the complex. And we skip the first two because we already know they're exact. So we just start from here, from phi0. And we immediately observe that, so the zeroth cohomology group, so H0 of F dot is the kernel of this map, right? But the kernel of this map is precisely the global sections as we observed here.
Maybe just 1 second. Is it clear that this is a cohomological complex on the for every x, or
For every
for,
topological space?
I thought that was an open set, but
I mean, yeah, you can
no,
also
okay.
just take any. I mean, X. Now I'm taking the full manifold. But yeah, in principle, you can just take something smaller, and then you have, let's say, the cohomology of that open set. I think it works because if you have a resolution, so some exact sequence, then this is equivalent to have an exact sequence at the level of stalks, right? And stalks are like a local thing. So yeah, as soon as you take some open set, like if you just restrict all these sheaves to the open set U, this is still an exact sequence because it is exact at the level of stalks.
Yeah, okay.
So yeah, you can take another set U here. Yeah, just an open set. You get a different cohomology, of course.
Yes. No, the question was sort of why are the phi axis differential? Like, why is going 2 steps always equal to 0? But
because this is exact, right? So at this level is exact. So we have simply the decomposition phi j plus 1 composed phi j. Sorry, j is the 0 map because this is exact. And this you can take it on any u, in particular on x. And this is 0, but this precisely means that the kernel of phi u j plus 1 contains the image of phi u j, no? Because everything that's in the image of phi u j, it's in the kernel.
yes, and
this is the definition of cohomological complex. I mean, cohomological complex, you only need this, right?
yes.
This is not the definition. The definition is this. You need morphisms of abelian groups such that if you compose 2 of them, you get 0. And that's it.
And no, my question was just why does the exact sequence on the level of stocks give that the sequence on the level of the whole manifold is a cohomological complex? But
I mean, remember the cohomological complex doesn't mean that it's exact, right?
Yeah, of course.
You just have one inclusion. And I mean, it's this thing here. I mean, just forget the stocks. Just the fact that this is exact means that phi j plus 1 composed phi j is equal to 0, right? It implies it.
Yes.
This is a composition of maps between sheaves.
Yeah.
But then in particular, it's true for every time we take a set U, which in this case we take X.
Yeah.
So now
because it's a functor. Okay.
Yeah.
No,
Yeah,
then
taking the global section as a functor, yes.
okay, yeah, now I understand. Thank you.
Okay, yeah, so what I was saying here is just having a look at the zeroth cohomology group. So what is this H0 of F dot? Well, this is the kernel of phi 0x. And yeah, by this observation here, the The kernel of phi 0x is nothing but the image of phi x, but phi x is injective. So I'm gonna just write here. So image of phi x, and here we write, since phi x is injective, this is nothing but the global sections of the original one. Yeah. Which we know already. It's the zeroth check cohomology of F. So we have this kind of recurrent thing that every time we take a zeroth cohomology, we always get the global sections. And to give you an example of an acyclic resolution, the Rham complex is an acyclic resolution of the locally constant sheaf of Rx. Locally constant sheaf. Yeah, and the Rham complex is simply the P forms. So in that case, our sheaf F would be the locally constant sheaf, and phi 0 would be just smooth functions. And then you have one forms, and then two forms, etc., etc. So we know that that one is exact as a sequence of sheaves. I don't remember if we proved it already or something we're going to do today, that every time you have a sheaf, which is a module over smooth functions, its cohomology is trivial. Did we prove this already? I think not. I think it's today's lecture.
I couldn't remember, so.
I think it's today's lecture.
Okay.
But yeah, so this is just an example for now. Maybe we don't know. Okay, I think it's clear. We know why it's a resolution because we already saw when we discussed in the RAM that is exact at the level of sheaves. But furthermore, we'll see today, I think, it is an acyclic resolution. And why are these resolutions, and in particular acyclic resolutions, important? Because of the theorem, which is the abstract, the Rham theorem. So we take a sheaf of abelian groups on X, and we take an acyclic resolution for this sheaf. Is it 0? So 1. Be an acyclic resolution. Then the kth cohomology of the cohomological complex of global sections is precisely the kth check cohomology group of the sheaf F. Okay. And if I understood your taste, I think you will like the proof. There's a lot of arrows and algebra. So we know it for k equals 0. Okay, this is this first line up here. H0 F dot equal H0 XF. So k equals 0, done. So the final idea will be to do it by induction. And this is the good okay equals 0. But before like looking at the precise induction we're gonna set up, we need to introduce a few other steps. So we make a new sheaf, K1, which is nothing but the kernel of phi1 in phi1. So we know that the kernel is a subsheaf. Okay. This gives us a new exact sequence. So Ki minus 1 is just, of course, injective into Fi minus 1 because this is a subsheaf. And we know since this is an exact sequence, that the kern K1 is precisely the image of phi I minus 1. So this is phi I minus 1, and here you get Ki. And this goes to 0. So this is exact. Yeah, we have a short exact sequence. And by the way we defined these objects, by definition, what is this hi of f dot? Well, this is nothing but the kernel of phi xi modulus the image of phi I minus 1 x. So this kernel, we can immediately replace it with global sections of Ki, right? And the image is just the image. Keep it like this for now. It will change very soon. And the nice thing here is that now we can think this Ki of x as the 0th check homology of the sheaf Ki. Right? So we have, let's say, a better understanding of what's up top, but what's at the bottom. So what is this image? Well, it's the image of the map that goes from Fi minus 1 of x into Ki of x. So here we are Fi minus 1 x. But again, these two can be thought as cohomology groups, as the 0th cohomology group of the respective sheaves. So you can think of this as the image from H0x Fi minus 1 into H0x of Ki. Okay. So this gives Hi f dot is H0 of xki modulus the image, and I want to write this image, in terms of 0th cohomology group. Okay, so for now we're just following the definitions and replacing all these global sections objects with 0th cohomology of something. And why do I want to put the 0th cohomology here? Well, because we have a short exact sequence of sheaves. Hence, we have a long exact sequence in cohomology, which is what we proved last time, yeah? And it was not so easy. So we have the long exact sequence. So now we're just, since we're only looking at the 0th section, let's just look at the first steps of this long exact sequence. The later steps will also be important. But let's focus on this one for now. And here we have this, the snake lemma map, which we know is actually not the snake lemma in this case, but close to the snake lemma, and we call it theta. H1x Ki minus 1. And then you would need to put H1 of x Fi minus 1. But if you assume that I is at least 1, this is 0 because the resolution is acyclic. So this is H1x F I minus 1. And fi minus 1 is cyclic. Okay, this is the motivation for this equals 0. Okay. But now this is great, because now what we get is that this last map is surjective, right? And as you know, this is just morphism of abelian groups. So you can use the isomorphist theorem telling you that the image is equal to the domain modulus the kernel, correct? And the kernel of this map is precisely the image of the previous map, because this is an exact sequence. So let's write it down. So the induced map, theta tilde, goes from h0 of x ki modulus the kernel of this map, which we know is nothing but modulus the kernel of theta, yeah, which is nothing but the image of this map. So we write image h0 x I minus 1 into h0 x ki into the image, and the image is everything because this last map is surjective. Okay, so this is an isomorphism. The map is an isomorphism. And now we're like, oh, wait a second. This is precisely the same object. No? So what we finally get is that hi of f dot is the first cohomology group of x k I minus 1. Okay. So, okay, interesting for now random fact. But right now we're playing only with this particular exact sequence, ki minus 1, fi minus 1, ki. But of course, this is true at every level, right? So the idea is to play the same game with ki minus 1 instead of ki. So just lower one more. So let's just do it all simultaneously. So let's take our r, which is between 2 and I. So we have 0, ki minus r, fi minus r, ki minus r plus 1. Okay, so this is just exactly the same as this. We're just basically renaming the variable I to be I minus r. Okay, so this is exact. So it induces a long exact sequence in cohomology. So let's write down this exact sequence. So here we have h. So now instead of looking at the 0th term, we look at the r minus 1 slash r term. So this is like the 0, 1 part. Now we look at r minus 1 r. So this one is 0, again, because fi minus r is a cyclic and r was greater than 2. So this is 1, so this is 0. And this one must go in r minus 1 x of this one. And now we increase the degree and we go back here. So hr of x ki minus r. And then you put the 0 again, because this would be just the hr of fi minus r. Okay, so again, we use the fact that the resolution is acyclic. So for now, we use the fact that the resolution is acyclic here, here, and here. So we're using it quite a lot. So we have an exact sequence with 0, element, element, 0. This means that these two must be isomorphic to each other. H r minus 1 x k I minus R plus 1 is isomorphic to H R X K I minus R. Aha, and now this is kind of perfect because you see, basically it looks like the only thing that matters is the sum of this, right? If I lower this one, sorry, if I raise this one and then lower this one, you get the same thing, correct? This means we can go all the way back to this. So let's just so HIF dot, I'm gonna rewrite it. This was H1 of X K I minus 1, right? We had it right here. But now, okay, take R equal to, and this is the same thing, right? Yeah. So we can do it again, and we get, I mean, in general, just all of them, right? You do it step by step, and you get all of this. For every R, I mean, not, it has to be greater than 2. I mean, also 1, because we just proved that it's also 1. But at most, you can get to I. Okay. But now take R equal I, and we get that this is precisely Hi of X of K0. But K0 is the kernel of phi 0, which we know because this is an exact sequence of sheaves, the initial one. Where is it? The initial one. So the kernel of phi 0 is precisely the image of phi again, and the image of phi is precisely F because the map is, the first map is injective. So this is nothing but the sheaf F. So we reach the end of the theorem, which tells you that this new cohomology is precisely the check cohomology for the sheaf F. And this is independent of the resolution. Yeah? The only important thing is that it's an acyclic resolution. It's very important that it is acyclic. Okay, so we know this nice thing now that if you have a cyclic resolution for a sheaf and you want to compute the cohomology, the check cohomology of this sheaf, you can simply compute the sheaf cohomology. Sorry, the cohomology of this cohomological complex. So cohomological complex of global section of that sheaf. Problem: why would acyclic resolutions exist? Sure, we have one. We have the Rham, so that's nice. We know that at least that one works. But it would be nice to have something like, given a sheaf, there exists you know, a resolution which is acyclic. It would be actually nice to have a very explicit construction, which is somewhat canonical. And luckily, that's exactly what we have. Space. We take again a sheaf. So the first thing we have to do is kind of, given a sheaf, find a sheaf which is acyclic. So the optic homologies are 0, which is somehow related to X, to F. And this is the so-called sheaf of discontinuous sections. So F, then in square brackets, you put the 0. Discontinuous sections. So we simply define it like this: f0 of u is simply all functions from u to the disjoint union of x nu of the stalks, such that f of x is in the correct stalk. And maybe now you're like, oh, but this is just the sections of the sheaf over u. Or maybe you try to remember that this is very similar to what we did when given a pre-sheaf, we wanted to associate a sheaf. So we took something really like this. The only difference there is that we added an extra condition, is that locally you're represented by one element, if you remember that.
Sorry, my internet was gone. What was the last sentence? Locally.
So in the sheaf associated to a pre-sheaf, so
Mhm.
I'm trying to draw a parallel between what we're doing now and what we did when we were trying to associate a sheaf to a pre-sheaf.
Mhm.
Okay, so if you remember when we tried to make a pre-sheaf, we did something very similar. We only add one little extra condition, which can be summarized by words without writing the whole technical thing, that these objects, these f's, must be locally represented by one function, by one section. Well, here, this is why they're called discontinuous sections. You only require that at each point you pick an object in the stalk, and that's it. There is no local representative, which somewhat represents continuity. You just take an element over each sheaf and you can just make a mess. And I mean, since there is so little structure, it's easy to see that this is a sheaf. And you can see F itself as a subsheaf. Okay. And the reason we introduced this sheaf of discontinuous sections is because this sheaf is acyclic. So for any locally finite open cover U, the check homology with respect to the U of this sheaf of discontinuous sections is 0 for every p greater or equal to 1. So in particular, this implies, of course, that the check homology without respect to a cover is 0. And the idea here is to use basically a discontinuous partition of unity. So let's see what I mean by that. Okay, let's take a cover. And we take T alpha, the family of disjoint sets such that X is the union of all of them. Okay, so these are not open. These are, this is, they're not closed either. Yeah. They're just something, we're just covering the set with these patches. Because they need to be disjoint. And such that this is true. And for every alpha, T alpha is containing U alpha. Okay. And we take rho alpha from X to, well, 1, 0, the characteristic function. Characteristic function of T alpha. So it's 1 on T alpha and 0 everywhere else. So this is my discontinuous partition of unity. Yeah, I want to think about it like that. Okay, so we need to prove that this sheaf is acyclic, so that this, so that this homology is 0. So let's just take an element. G alpha 0 alpha P. And we take this to be a P cochain of our F0. So sorry, a P cocycle. So we also ask, of course, that its delta is 0. Okay, so now we need to find the preimage. Well, first of all, we can extend each G alpha 0 alpha P to a global section, which is something you cannot do normally, but here you can just post 0. For X outside. Yeah, so if you are in this open set where you're defined in principle, you just stay yourself, and everybody else you just post 0. And this is perfectly legal because these sections are discontinuous. You just need that over every point you stay in the stalk. This is a sheaf of abelian groups, so every stalk has a 0. And you just post that. And that's very easy to define F. Alpha 0 alpha P minus 1. Simply the sum over beta of the characteristic functions times G beta alpha 0 alpha P minus 1. So first of all, let me just observe that the sum is finite for every fixed point. Yeah, because the covering was locally finite and T alpha is contained, or T beta is containing U beta. So over every point you have just one of these functions non-zero. So this does give us that, so this is well defined. It's a well-defined P minus 1 cochain. And to verify that this works is an exercise. But as a hint, we'll do the case P equal 1. So verify that delta of F alpha 0 alpha P minus 1 is precisely G alpha 0 P minus 1. Let's just do the case P equal 1 for, at least we believe it before we move forward. So what happens here? Say at the point at the index alpha 0 alpha 1. Well, this is just FA1 minus FA0, right? This is the definition of the delta. And now we replace this F alpha 1 and F alpha 0 with the definition. So we get the sum in beta of rho beta G beta alpha 1 minus G beta alpha 0. But okay, since the delta is 0, G beta alpha 0 is equal to negative G alpha 0 beta. So you have beta alpha 1 plus G alpha 0 beta. So again, this is just because it's a cocycle. And now you know that, again, because it's a cocycle, G alpha 0 beta plus G beta alpha 1, this is nothing but G alpha 0 alpha 1. And if you're like, oh, I don't know if all of this is true, G beta alpha 0, it's equal to this, like that you can just revert the index and add the negative sign, and if you sum are like this all comes from the fact that they're a cocycle, but maybe to be a bit more convinced about it on the spot, remember that for a 2 cycle, so for a 2 cochain, to be equal to be neutral element in multiplicative notation. So now we're using additive notation, but in multiplicative notation is the same as asking that these are transition functions for some line bundle, right? So all these things we're doing is just think that these are transition functions for a line bundle, but we use additive notation instead of multiplicative one. Okay. Otherwise, you can just compute the thing and it all just works out. And now, okay, in the sum, this part is not dependent on beta anymore. So this is G alpha 0, alpha 1 times the sum, but the sum is identically 1 because these were characteristic functions over a set of these joint sets. So, only one of them is non-zero and it's equal to 1. And so we get what we wanted. Yeah. So this is for the case p equal 1, and I'll leave to you the general case, which of course is very similar. Just have to write this sums in a bit uglier way and realize that you do in fact use this cocycle condition somewhere. Okay, so given a sheaf, we have an associated sheaf, which is a cyclic, this sheaf of discontinuous functions. So we want to use this fact to build an acyclic resolution. So to build a resolution, we need some kind of exactness. So you have f, then you have f0. The next thing will need to contain, not b, but will need to contain the quotient, right? So let q0 be the quotient sheaf f0 mod f. And well, so now we need something which is a cyclic and that contains q0. So we take f1 to be the sheaf of discontinuous sections of q0, right? So now we know that this contains q0 as a subsheaf, which will be, of course, the image in our resolution. And this is a cyclic because it is a sheaf of continuous function of discontinuous sections. So it's a cyclic. And then we just continue. So then let q1, well, q1 will be simply f1 modulus q0. And f2 with the square brackets will be nothing but the sheaf of discontinuous fractions of this q1, etc., etc. So let's say write down some sequences which are exact. So these are exact. So f goes into f0. So we know this is an injective map because it's just a subsheaf. And what do we put here? Well, here we have to put the quotient, right? Which we called q0. So this was our first step. And now we can just repeat using q0 instead of f. So here we have q0. Then we take the sheaf of discontinuous functions of q0, which gave it a name, and that is f1. And here we put q1. And in general, you're going to have 0, q p minus 1 into f p into p. Yeah, these are all short exact sequences, simply by definition. Yeah, you have a sheaf, you have a subsheaf, and you just take the quotient. But this means that now if you take this thing, this is exact. Okay, just think about it for a second. But if you look at it, okay, you have, okay, this map is injective because we already have it here, for instance, no? And the image of this map is precisely Q0. But we know this is also the kernel of the next map. Okay, so the idea is like here in between, you have all these QIs. Let's just think about it like this. Here you have your Q0 in between. Here you have your Q1 in between. Yeah, and these maps are the quotient maps, and these maps are just inclusions. So this would be the kernel equal image object. So this would be the kernel, and it's also the image. Okay, so it's the kernel of the successive map, and it's the image of this map. So we have this exact sequence, and yeah, we already know, we know that the cohomology of the sheaf of discontinuous sections of any sheaf is 0. So this is an cyclic resolution of F. And by the previous theorem, abstract the Rham theorem, we also get that the pth check cohomology is the same as the cohomology of this complex, of the complex of global sections. And since, you know, we made this construction, this has a name. So this resolution is the canonical flabby resolution. And I think flabby really comes from the fact that these are all discontinuous sections, so they're flabby in some way. I promise I didn't come up with this. This is the official name. Okay, so maybe let's, before we move on, let's just review what we did so far today. Okay, so we started okay, by defining what a resolution is and what an acyclic resolution is. And we proved the abstract, the Rham theorem, which tells you that if you do have an acyclic resolution, then the check cohomology of the initial sheaf is nothing but the sheaf of the cohomological complex obtained by taking global sections. Okay. And then, of course, the next question is, okay, so now we know this thing, but we don't have acyclic resolutions. Theorem, we do have acyclic resolutions. And this is the acyclic resolution that comes from this discontinuous, from this sheaf of discontinuous sections. Okay, so we define what is this sheaf of discontinuous sections. We proved that it is indeed acyclic. And then we showed that using it, one can construct this canonical flabby resolution. Okay. Fortunately, there is actually a better way to do this, because this is very abstract. You know, this F0 is all discontinuous sections. Okay. And then you have to take the quotient by continuous sections, and then take the discontinuous sections of that. And then you have to compute kernel modulus image. This doesn't look trivial. So fortunately, we do have better ways to actually compute the chronology. I mean, this is a nice theoretical result. It is constructive because, you know, you can just take, oh, we have the discontinuous sections and we take a quotient, but it's not something you're going to ever use to compute cohomologies. There is another way to compute cohomologies. So again, we start with a paracompact topological space, and we take a sheaf of abelian groups. Next. And we take a locally finite cover, locally finite open cover. And we say the U is Leray. I'm probably mispronouncing it. For F, if for all non-negative m's and all indexes of m plus 1 elements and all p greater or equal than 1, we have that the pth cohomology of this intersection is 0. Okay. That's how we call it. So it is some kind of acyclic. I mean, acyclic is a generic term which is used whenever some cohomologies are 0. And just one thing I want you to recall is that for any sheaf G, we always have a map from the check cohomology with respect to a cover to the general check cohomology. Okay, this is a map, and we know that it is a map. And okay, why are Leray covers important? This is the Leray theorem. Okay, we take a paracompact sheaf U locally finite array. Then this map, this induced map, is actually an isomorphism. Okay, so what it's telling you that if you take your cover to be good enough, then to compute the check homology, you can simply compute the check homology with respect to that cover. So this is now something which really can help us compute cohomologies. So now do we prove this? We will still consider the part of this. So we'll still use this sheaf of discontinuous section. And what we want to prove is that this cover is also Leray for Q0. So we want that U is Leray for Q0. Okay. So I don't want to write U alpha 0 intersected U alpha M every time. So let's just call it V. And then, as you kind of observed before here, to have a, you know, we don't have to take X, we can just take V. And we know that every time we have a short exact sequence of sheaves, this gives a long exact sequence in cohomology. And then, yeah, so if you restrict these sheaves to V, what you get is HPVF0, HPVQ0, HPVQ, HP plus 1 VF HP plus 1 V F0. Now these two are 0 for P greater than 1 or equal than 1, because we know that the sheaf of discontinuous sections is acyclic. So we have an isomorphism again. So HPV Q0, it's isomorphic to HP plus 1 VF. But now this is 0 because U was our Leray cover for F. Yeah. Definition of Leray cover. So we're good. So, I mean, we're not done with the proof, of course, but we do prove this claim. So, which is that U is, if it's Leray for F, it's also Leray for Q0. So that's one step. And so in this Longet sequence, let's actually look at the case P equals 0. So global sections. Yeah. We look at P equals 0. And what we get is this. And then here, what we should get is H1 of XF, right? Sorry, VF, because we're taking everything restricted to V. But this is 0 again, because U is the ray. So what we have now is that this is a shortest X sequence for every V. Remember, this is for every V. V was one of these intersections. Where is it? Oh, did I delete? What? Did I make a mess? Okay, I swapped page 7 and 8. I have no idea how I did that. But sure. Okay. Yeah, so this V was just any of these intersections, right? We'd just say, hey, v, let's take V, this intersection, but this is arbitrary. So if this sequence is exact, 0 FV, F0V, Q0V, 0, then we also have, so V arbitrary. We actually get that the full complex of cochains is exact. Yeah, because anyway, the operators here are defined separately on each open set V. And so if it's true for each of these V, it's also true for the full collection of them. And we know, so now we have a short exact sequence of cohomological complexes, right? And so we have a long exact sequence in cohomology. Et cetera, et cetera. So again, let's just look at it for P equals 0. Well, we know that H0 hat of U of G is G of X, right? And this is the same at H0, X of G. This is for any G. So phi 0 is an isomorphism. I mean, this is true for any U. We don't need, in this case, we don't even need the ray. It's just always true. Okay, so now let's look at P equal 1. And now it is interesting. So we have this diagram with exact rows. H dot 0, U F 0, H hat 0, U Q 0, H 1, U F. And now here we would have H1 hat U F1, but we have a Leray cover, so it's 0. So this is one of them. And the other exact sequence we have is this one. And again, this is Leray. Sorry, no, this is not Leray. This is the fact that F0 is a cyclic, always. Okay, so we know that these are exact because, I mean, this is always true whenever you have an exact sequence of sheaves. Then you have a long exact sequence in cohomology. Well, this one we actually have to prove that was exact. And this comes really from the fact that U is Leray not only for F, but also for Q. Q0. And now here we have on this direction, we have the direct limit maps. And this one we know is an isomorphism. And this is also an isomorphism. Why do we know this? Well, because this is just the zero section, the zero term. So this is just global sections. Yeah, so this is what we wrote here. For P equals 0, these are isomorphic for any sheaf. And we don't need the Leray, we don't need anything. And here we have this map phi1u, which we wanted to prove is an isomorphism. So you have this diagram with exact rows, and the first two downward arrows are isomorphism. You have to prove that the last one is an isomorphism as well. So I believe since you told me you did some cohomology already, you saw the lemma of the 5. The 5's lemma, something like this.
Yeah, I did.
So you know the technique of proof here.
Yeah, I think this might even be easier.
Yeah, this is easier because this is just one little step of the, I mean.
Just a small diagram chase.
Yeah, it's a smaller.
I don't know, is that an English word?
For
yeah,
diagram chase?
Yeah, that's what we say. Okay, yeah.
Yeah, diagram chase is the English word for it. Okay, so we have the case. So we have this case P equals 0. They're always the same, no big deal. For P equal 1, we have this diagram with, I mean, you can think that this is ISO. We don't know. ISO, just with zeros. Just put one more 0 and use the lemma of the 5. If you know the lemma of the 5. If you don't, it's an exercise. Okay, so now we have to prove for all P's. So for pre-graded, we use induction. And this is actually easier. Because again, we have exact rows on another diagram, which is easier because it's even 0, HPU, Q0, H hat, P plus 1, U, F, 0. And here we have zeros because the sheaf of discontinuous functions is a cyclic. Also here. Because here you should have the pth cohomology of the sheaf of discontinuous, and here P plus 1 of sheaf of discontinuous. So as P is greater or equal than 2, this is just 0. And well, this is an isomorphism. Why is this an isomorphism? This is by the induction. This is where we use the induction. So we're assuming that it's true for P, right? And we're using the fact that the U is a Leray cover for Q0. So our induction is saying for every P, if you have a sheaf and a Leray cover for the sheaf, then this map is an isomorphism. Okay, so this is an iso by the induction thing. So that's why we had to prove that U is indeed a Leray cover for Q0. Otherwise, of course, here you don't have anything. And here you have this map, which, okay, is the one we want to prove that it's an isomorphism. And this is, again, an exercise. This is, I mean, this one's even easier. Okay. So this concludes the proof, and it tells us what is the importance of these Leray covers. Okay. There is something else to take away from this proof. So before we move forward, every time we have a locally finite open cover U, the first map, and just the first map, so not for any P, but really just the first one, this map is always injective. Yeah. So this is nice. And let's see why is this true. So before we had 0 CPU F CPU F 0 CPU Q0, and then we had the 0, right? So I'm just gonna go back where? Yeah, and then here we had the 0, and the reason we had the 0 was because this cohomology group was 0 because we had the Leray cover. Okay, but now if you just take a generic cover, here you don't get the 0 anymore. You get something else. But if you replace this last object with just the image of this morphism, you still get an exact sequence. So I'm going to go to CPL. Exact. So if instead of just putting what there was in the proof, we replace this with whatever is the image of this morphism, this is of course an exact sequence. They're artificial, but it's there and it exists. And now we can, now we can continue. We get, so this is still an exact sequence of cohomological complexes. So we still get a diagram with exact rows. Just that instead of here having the correct thing, you get the cohomology of this complex, the one with L. So these are exact rows. And below, of course, you have exact rows. H1, sorry. So here we have exact rows. This is an isomorphism because this is just the 0 sections. I mean, the global sections. This map here is the inclusion. Inclusion. Why? Well, because you can think, so this CPL is contained in CP. So we have an inclusion map between this, which of course it's also a map between cohomological complexes because everything commutes with the delta, it's just an inclusion. Okay. So you have this cohomological complex included into this cohomological complex. This implies that the cohomology of this cohomological complex is contained in the cohomology of this cohomological complex. Here you take the direct limit So you get also an inclusion here. And this is our phi 1u. So you exercise again. You have this thing, and this is an isomorphism, this is an inclusion. Prove that this is also injective. So isomorphism, injective, map, 0, exact rows implies that this is injective. Okay. So this is just an observation in the sense that it's not something you probably will use a lot. And it's also an observation in the sense that the proof is missing some steps, clearly. So you made a bit of a, not sure about what you're saying phase. So for instance, you have to prove that the CLP is in fact a homological complex. So what tells me that, you know, if I take something in the image and I take the delta of it, it's still in the image of the next step. You know, in principle, if you take the delta of something in the image, you're just going to see p plus 1u without the L. So you have to prove that. So you have to prove this is a homological complex. You have to prove maybe in fact that, okay, the inclusion part, it's easy, but you know, once you go in homology, you're not given that. I mean, if you have an injective map of homological complexes, the fact that this is still injective in homology is not trivial. And here we're even taking the direct limit after that. So, oof. Yeah, not clear. So maybe proof, the proof is just a sketch. Sketch. It's really okay. Sketch. Okay. Yeah. So we have one last theorem for today, which would really give us some very powerful tools to compute all the homologies we like to compute. So we already saw this theorem for the Rham homology. And this is the Mayer-Vietoris theorem. Yeah. So again, it's a theorem which tells you that if you can decompose your space as two open sets, there is a relationship between the homology of the intersection, the sum of the homologies, and the homologies of the whole space. So our X will again be paracompact and Hausdorff topological space. And we decompose it into open sets. And we take a sheaf on X. Then we get the same longitudinal sequence that you get in the Rham homology. So HPXF goes into HP of U, F restricted to U, of course, plus HPV, F restricted to V. And here we have HP U intersected V, or F U intersected V, and then we rise. And you keep going. And the sequence is also exact. So the idea here is actually find, so of course these homologies, we will see them as three distinct homologies. So you have the homology of X, the homology of U plus the homology of V, and you have the homology of U intersected V. And we'll think of this as three distinct homological complexes, and then find a morphism of homological complexes, which is exact. So let's do it. So we will again use our canonical flabby resolution. Be the canonical flabby resolution. And now we consider three distinct cohomological complexes. The cohomological complexes. So we have this one, which is the one which we know by the abstract Rham theorem actually gives us the cohomology, this cohomology here. Then we have f dot u plus f dot v. And then we have f dot of the intersection. So these are three distinct cohomological complexes. And okay, we actually know for sure that the cohomology of this complex by the abstract Rham theorem is this cohomology, and the cohomology of this complex, again by the abstract Rham theorem, is this cohomology. So, and of course, what we expect is that the cohomology of this complex is this cohomology. But before, so to get a long exact sequence, what we need is a long exact sequence. Sorry, it's a short exact sequence of complexes, right? So consider for p greater or equal than 0, 0, fp x theta fp u plus fp v eta fp u intersected v. But of course I have to tell you, so that's what I want, and I want this to be exact, but I have to tell you what are theta and eta and prove that then this is exact. So with theta of s, easy, we just restrict the two sides. Yeah. While for eta, with two entries, we send it to the difference. Okay. Claim it is exact. Okay. So, I mean, before we prove the claim, let me just repeat if true. And then we are done by the abstract Rham. Yeah. Is this last part clear? Because if this is because then if this is true, then this is a short exact sequence of cohomological complexes. So we get a long exact sequence in cohomology, but we prove that let's say, oops, misclicked. But we prove that the HP of F dot, which is the cohomological, which is the cohomology of this complex, for instance, is isomorphic to HPXF. Yeah, so you simply replace all of these objects here with what we have here. So you can have restricted to U plus restricted to V. This is isomorphic to HP of U F restricted to U plus HP V F restricted to V. And also for the last one, yeah? So you just replace each one of this and we're done. So I have to show that this is exact. And fortunately, that is not too hard. So theta is injective. This is easy. Yeah, because simply remember that theta of S is SU SV. So, I mean, if these are both zeros, then of course S was 0 from the start because we're in a sheaf. And we also get that the image of theta is the kernel of eta because FP is a sheaf. So maybe let's show this. Of course, if you compose eta compose theta of S, this is theta of S restricted to U, comma S restricted to V. So this is just S minus S. So one direction is easy, right? So this implies that the image is contained in the kernel. And vice versa, eta of IAB equal, what's it, A minus B restricted. Implies that A and B glue to a section on X, right? So you have a section on U and a section on B, and they are the same on the intersection of U and V. So there exists a section S such that if you restrict it. This is the second property of sheaves. Okay, then why is eta surjective? And then we're done. And it's also easy because FP is a sheaf of discontinuous sections. Continuous sections. So again, given something here in the intersection, we can extend it to 0 on U, and then we get eta of S tilde. 0 is just S, and S tilde was this extension. Yeah, because in the end, you're only going to look at what happens when you intersected V. So you get S tilde restricted to U intersected V, and this is just S minus 0. So it's surjective. So we're done. Okay, so this concludes today's lecture. So I think this week we did some pretty hard stuff, which are somewhat the top of this course. We defined the check homology and proved quite a lot of properties about it. And we proved this abstract Rham theorem, which is what links, let's say, all homologies to each other in a way. So next week we will see more applications of this sheaf homology directly to things we already know. So we will link pretty much what we did so far with what we did in this week. Is there any question about today's lecture?
I think I had two little questions. We showed that there is always this flabby resolution. I know, maybe that's stupid. Is there always like a Leray covering, or because we used it?
That depends on the sheaf.
Okay.
So we will see next week that I don't remember exactly the result, but for the sheaves we care about, yes. So for instance, I think for the Rham complex, the important thing is that all these intersections are contractible, for instance.
All right.
And then there you get, yeah. But that is because we know that the Rham homology is homotop invariant. For an abstract sheaf, no, this is not so clear.
Okay.
I believe it is not true. I'm not certain, but I'm pretty sure it shouldn't be true that there's always a Leray cover.
Yeah. Okay. Okay. Well, and the other question was sort of like strategy. The Rham, the abstract Rham theorem. did we do it to understand the check cohomology better, or is it just a very nice result for every cohomological theory?
I think that question will be answered better next week, because we
All
will
right.
see like all this relationship. For now, yeah, I mean, it's just nice isomorphic theorem that tells you that our check cohomology can also be seen as a cohomology of some complex. But what this means is that every time you have a sheaf, if you manage to find a cyclic resolution for it, then you get the cohomology. Then you get this isomorphism of cohomologies. Because then you see this, where is it? This HKF dot, which now looks very abstract, because what we took here for us was the flabby resolution, which is like, who knows? But if you actually find something which has some geometrical meaning, like the de Rham cohomology, this object here is precisely the de Rham, becomes, so when you apply this theorem to the de Rham complex, to the de Rham acyclic resolution, this object here is precisely the de Rham cohomology, like defined as usual. So what you prove is that the de Rham cohomology is the same as the cohomology of the sheaf of constant functions. Of locally constant functions. So this is definitely something strong.
Okay.
So for us, it's just this, but the idea is that this object can be something nice, something that we can compute, something that we can link to other things. So yeah, we will see this for the de Rham cohomology, and we will see this for the Dolbeault cohomology. Do you know what that is?
I do not. So
Well,
the idea is more or less okay. Yeah, that we will find out about very nice resolutions, so to say.
Yeah, I think that, at least two of them we will see. So
All right.
the Rham and this Dolbeault, and we will go back to the Picard group again. There's, and we will see divisors again. This divisors are somehow linked with the Picard group, but now we know that the Picard group is the H1 of never zero functions, right? So, well, you're H1 of a sheaf, but then we know that this must be somehow linked to some resolution. There's going to be a lot to say. In fact, it's going to take the whole week. It's not one lecture. It's the whole week.
All right. Then I'll revisit everything we've done so far. And yeah.
Okay, perfect. Then I'll see you next week, and have a good weekend.
Have a nice weekend. Bye.